we are at the brink of a very, very exciting time as we go forward in science. And I want to share that excitement with all of you so that hopefully I can do a little bit to inspire some of you to really pursue a career in science. That's the aim of my talk today, okay? To at least stir some interest. Some of you already are interested. In that case, I hope I can add a little bit to your interest. Because I really do think that what lies ahead is a very exciting few decades where there is going to be remarkable progress in diverse areas of science, ranging from cosmology, the study of the universe on the biggest of distant scales, the longest of time scales going back to the Big Bang. That's the kind of area I work in myself. High energy physics, where we probe what happens deep, deep inside the atom, inside the nucleus of an atom even, where India participates in some of the key leading experiments, and I'll tell you a little bit about this as we go along. Remarkable progress in material science, as we understand more and more about quantum mechanics and novel kinds of materials we can build. That connects to chemistry, and of course biology, which really in the 21st century I think is going to come into its own as we understand the entire interplay between genetics and life and the mind and brain and so on. What lies ahead is truly fascinating. Now, another very important thing to keep in mind is India's GDP is growing, and as India progresses, we are bound to invest more in science. Okay, our country's progress is never very, direct and monotonic like China's is. Often the comparison is made. It's true. We have our bumps and fits and starts. But what I want you to take today is a broader perspective, because your whole life lies in front of you. And if you view India's progress in a broad perspective, you'll see that we do the right things, okay? More or less. And so I think it's a matter of how GDP is bound to grow because of all the bright young people, right? 300 million young, bright people in this country. No one can stop us. And as we progress, the country will invest more and more in science. So that means young people in India are going to have the opportunity to participate in this remarkable progress in very significant ways as the country invests these resources. This is a remarkable opportunity. It's also a very important challenge in front of your generation. I say challenge because if you look at all the key problems facing India today, I would say to you, in one way or another, they are integrally and essentially connected to science. If you look at health, if you look at agriculture, to increase our productivity, look at energy, it's such a key issue, right? Our petroleum reserves the world over are going down. What do we do? Solar, new kinds of nuclear, something else, okay? Environment, such a key issue with all the carbon dioxide, global warming and so on, connected to energy. All of these are of course crucially tied to science. And it's very important that your generation finds answers to these problems, if not only India, all of humanity is to go forward. So it's a great opportunity, but also a very important challenge which you have to face up to. And I'm sure you will, but you need to be excited about it. This is also true more generally, besides what I listed, about the whole world. And as I said, the written here, the United Nations recently listed 17 sustainable developmental goals, which India has also embraced. I don't know how many of you know about these goals. Anyone know these sustainable developmental goals? Okay, I'll show you what they are. Never mind. Till I became an administrator recently, I didn't know what they were. Then once I went to the Planning Commission, Niti Aayog, and they were all talking about it. I had to Google what are these sustainable. Google can be very helpful sometimes. I'll share them with you. But it's very, very important. The United Nations has put down these goals. India has embraced them. You'll see almost all of them really require new progress in science. Okay, important transformational change, which can only come from science. Technology is important too. Technology and science are connected. Actually, there's no real divide between the two, right? But what's important about science is if you want transformational new ideas, okay, they come from science. Because what science does is go after understanding at a deep level the basic fundamentals of how nature works. And from that deep understanding comes radical change, right? That's why science is important. And okay, here they are, poverty, hunger, good health, quality education, gender equality, clean water, clean energy, so on and so forth. You'll see how many of them, even some which don't seem like they're connected, climate action, in the end when you think about it, are connected one way or another with science. So therefore big challenges and huge opportunities. It's clear that in your lifetime, as you come of age now, science is going to shape the world, and therefore you have to rise up to this challenge. It's a remarkable time actually, and I really hope you will, many of you will embrace this opportunity, especially if you have the opportunity to study in such a great college as Hind College, right? Because your foundations are going to be strong, as we were talking, and with that strong foundation, you can do anything. Okay, so I want to give you a bit of an introduction about some of the kinds of science which are going on. I want to emphasize to you, the other thing I really want to tell you is that great things are happening in science in India. But this is important to say because, we read often about what's happening in the US, what's happening in Europe and so on. But actually, remarkable things are happening in India. Okay, and we should all be proud about that as Indians, but actually I say that more here because that is the kind of opportunity you're going to get if you work in India in science. So I want to show some examples. My examples, I must say, a little biased because they mostly come from the Tata Institute of Fundamental Research where I do my research, okay, and where I work. But that's not to say that there aren't equally, if not better examples elsewhere. For example, in BARC. Okay, for example, in IIT Bombay, or in any number of remarkable institutions across the country. And then we like to do. Okay, so let's look at some recent examples. Here we have an antenna from the Giant Meter Wave Radio Telescope. This is actually one of 30 antenna. This telescope has been built by TIFR, and it is located about 2 hours away from here, in a place called Narayangam. And the first thing I want to do to all of you is invite you to come and visit this telescope, because it is the best telescope in its class in the world today. Okay, it literally is the best. I'll show you some data. Not only today, it went through a recent upgrade, after which I'll show you the comparisons. It's going to be the best telescope of its kind in the world for about the next decade. Okay, next decade. So an Indian scientist working on this telescope has the opportunity to understand the secrets of the universe in a way you can't get anywhere else in the world. Okay? So this is the kind of opportunity India holds for you today. Now, so here's a bird's eye view. This is the GMRT, Giant Meter Wave Radio Telescope, operated by the National Center for Radio Astrophysics, which is a part of TIFR. As I said, about 2 hours away from here, there are 30 antenna because that allows us to combine signals, and by combining signals you get greater sensitivity. A little bit like how you can do better with 2 eyes instead of 1, here you do better with 30 antenna. Okay, so that's the basic idea. And the building of this telescope really goes back to Professor Govind Swarup, one of the pioneers who was a scientist who worked in TIFR. And it's not only a great example of science, it's also a wonderful example of made in India and frugal innovation. Because this telescope has been built at a fraction of the cost, about 100 the cost of comparable telescopes elsewhere in the world. Combining Indian ingenuity with what we can do easily in India, putting it all together. Okay, so it's a very good example. Now here I want to show you a plot. This plot is a little complicated, but look at the blue dots. That is our telescope GMRT. It went through a recent upgrade, after which the sensitivity has roughly gone down here, which is the upgraded GMRT, the improved one. And basically in this plot, the lower you are, the better you are in terms of sensitivity. Okay, that means your telescope is doing better. You will be able to see sources which are fainter if you are further down, because the required amount of luminosity goes up. Okay, so that's the plot, and you'll see various competitors. The VLA is here, the JVLA is in brown, and so on. And you see we do actually very well compared to that competition. This is the competition until the stars come online. That's the square kilometer array. That's a decade or so away. And actually, we have been invited, because of our experience with this telescope, to be one of the key international collaborators on the square kilometer array as well. That won't be located in India, it will be in South Africa and Australia, but we will be one of the key collaborators. But first of all, that's away for a decade, so we have a free ride to look at the universe in ways never explored before. But even after that comes online, India is going to be a key participant. Okay? So there you are, see how well we are doing, and these are all great opportunities. Amazing things have already started happening. The upgrade got completed about a year ago. Here's a study on the southern sky of pulsars. Pulsars are very interesting radio sources, very fast rotating neutron stars. And a large number of them, never known before, have been discovered. We are hoping to learn more about how these fast rotating stars work and so on as we go ahead. Okay, here's another kind of interesting use that you might find amusing. About a year ago, we were contacted by the European Space Agency and by NASA, and they were putting a mission up to Mars, and the mission had a landing component which was going to land in Mars, and they wanted to track it for the last crucial 8 minutes or so as it descends down. And they looked around and they found that the GMRT was the best telescope to do that last tracking. And so they got in touch with us, we were happy to collaborate. And here is actually the ESA mission. And unfortunately, that mission didn't make it down to the surface of Mars because as it landed too hard and crashed. It wasn't a successful landing, but that just gives you an idea of the kind of sensitivity we can bring to bear for this kind of a task. Okay, let me turn to another example, which is also I found very inspiring. It's terrible for any scientist to become an administrator because you want to be doing your own experiments, now you have to sign files, right? But it has its moments. And for me, one of the great moments was that in 2015, I was invited to witness the launch of a PSLV rocket from Sriharikota, right, in mission control, almost right next to the scientists actually operating the controls of that mission. And the reason I got this very great and rare privilege was this rocket was carrying Astrosat, which is the first satellite India has built dedicated to space astronomy. And TIFR, I must apologize, this is going to sound like beating a drum, I say that really, but the examples which come readily are the ones I'm giving. The TIFR built 3 of the 4 payloads on that satellite. Okay, the payloads were dedicated to X-ray astronomy. Previously, what I talked to you about was radio telescopes, so in the radio frequency range, X-rays, as you know, are much shorter wavelengths, right? Almost the opposite end of the spectrum. So these instruments look at the universe in that opposite end of the spectrum in X-rays, where also the universe is very close. And so the satellite was to go up, and I was there, and it was a picture-perfect launch. Astrosat was one of the satellites, but there were 8 other satellites which were released. 6 of them were not Indian, and it's amazing. They plot the trajectory, expected trajectory that the rocket will follow beforehand on a big screen, and then there's the dramatic countdown and the launch occurs, and then they plot the actual trajectory. And you could not tell with your naked eye any difference. All the way through, the launch goes, the 8 satellites are released, the rocket continues, finally goes over Indonesia, finally falls into the sea. It was exactly as they had planned and calculated. It's really remarkable. I was very happy to hear that ISRO has now begun to start inviting people, especially students, to go witness these launches. And really, if there's one opportunity you should take, I hope your college can provide it, it is to go. It's not so far away after all, it's 2 hours from Chennai. And it's very, very inspiring. You feel very proud. I feel very proud. Okay, now here's another very important picture, okay? Yes, this is not the Astrosat launch, the Mars mission which went up Mangalyaan, but it's similar for all the launches, right? And I hope you're noticing something here, right? And I hope you're all noticing something here. See, this is equally important, I think, as important as that picture perfect launch. So this too is happening in India. I don't think quite, I might not be right, but I don't think it's quite as good in NASA or ESA. And this is something to be really proud about, that we've done this in India as well, right? We have women in key roles. In fact, the person who was the mission chief for the AstroSat mission, Dr. Sita, someone who came up through the ranks, she was the mission control chief. She in charge of that entire mission. So amazingly competent, not just a lot. So I think this is also really very, very inspiring. I'll tell you a little bit about the instruments. We built 3 instruments, as I said. The LAX PC, this is a proportional counter which counts the number of X-rays that come, but it has a very good rate for counting, and it can collect a large number of such X-rays. The soft X-ray telescope SXT, and this is the oddly named cadmium zinc telluride imager, which uses cadmium zinc telluride crystals, etc., to image X-rays. And it's always tricky to have a payload go up in space, because you build it in the laboratory, you test it in the laboratory. Of course, ISRO has very stringent controls. They then take the payloads, they shape them, move them. They have to be space worthy. But even with all that, you're always got your fingers crossed, because once it goes into space, it's completely out of your hands. It's not like a laboratory experiment. Something doesn't work, you can't go up and fix it, right? So we were all very, very apprehensive, and but very happy to say when they were tested finally in space, they performed and actually did better than specifications. So it's been, as I said, now a few years. They're doing very well. All kinds of amazing things are being learned about the universe. I'll show you one picture here. Just roughly think of this as a signal in time, and there's a burst, and then there's a burst. So intermittent bursts which are going on, and this is supposed to be a very cataclysmic kind of event. There are 2 neutron stars orbiting each other. One is heavier than the other, so it's pushing material from the lighter one because of the stronger gravitational field, and that material which is falling on the neutron star, leading to a kind of nuclear explosion as it falls. Okay, and that explosion, which happens periodically, are these bursts which are coming out. And so that's the kind of event you have, and then you can study it, learn more about neutron stars, learn more about nuclear physics, underlying the behavior of these neutron stars, all kinds of very exciting things. So that's something we are doing, and we hope to learn more as we go along. Now I'm going to change gears and give you an example of something else, very different kind of physics. This is India's involvement in what's called the Large Hadron Collider. So the previous 2 examples I gave you were experiments we built in India, we are doing in India, and so on. But the arena of science is global today, and you don't want to be left behind. And so when it's needed, India collaborates with the rest of the world. And there are many examples. CERN is one example. The ITER experiment, where people are trying to achieve fusion, is another example, and so on. I'll give you this example of CERN. At CERN, what we have are 2 very, very high energy beams of protons that collide together, okay, at an energy of about 10 TeV, tera electron volts, okay, which is very, very high. It's the highest energy collider in the world. And basically, if you know a little bit of quantum mechanics, okay, then the higher the energy, roughly the shorter is the wavelength you can throw, okay, because E equals h nu. And so if energy is higher, frequency is higher. If frequency is higher, then wavelength is smaller, okay, because lambda times nu is the speed of light, which is fixed. So it's like a very, very high resolution microscope that you have. And what they do with this microscope is look deep inside the atom. Okay, as you all know, in the atom we have electrons, and then we have a nucleus. But what's inside the nucleus, right? So you look inside the nucleus, you've got protons and neutrons, but what's inside the proton and neutron, right? And so you can look inside, and you've got quarks and gluons and all kinds of other exotic things. And that's what they're trying to do and find out. And Indian scientists have played, including TIFR, the Dart University, BARC, number of institutions, Sama Institute, have played a very, very important role. There was one part of the picture, sorry, The detector, I should have had a picture, is very, very complicated. It's about 10 stories high, huge detector, many, many components, and a key component, which is a Hind calorimeter, is in fact built in India. Great contributions of the ARC and Indian scientists, and it's done very well. And played a key role in actually a very, very important discovery for which a Nobel Prize was awarded, and this is the discovery of the Higgs boson. The Higgs boson is a very important subatomic particle which holds the key to a number of very, very important secrets of the subatomic world, which I can tell you about at some point, perhaps not today. And this was, detected in events. It's very complicated because when you collide things, all kinds of mess comes out. It's a little bit like colliding two clocks and then looking for some tiny deer in the end, right? And all kinds of junk is coming at you. You have to be able to figure out, this is uninteresting, this is not interesting. This is the interesting piece. And that requires a lot of ingenuity. But that ingenuity was developed by scientists all across the world, and we led to this discovery. And the equipment we built actually here played a very, very important role in that. The experiment is closed down right now because the detector is undergoing an upgrade, and India is participating in that upgrade as well. Okay, let me give you, I know this is perhaps more a chemistry audience, I'm going to come to chemistry, but since I'm a physicist, you've got to start where your passion is. So, India's contributions in theoretical physics are well known, you all know about this. Mathematics, theoretical physics has always been great. Satyendranath Bose, you all know, I think, remarkable contributions. Just around the time when quantum mechanics came on the stage, he did this work, almost by himself, and then wrote to Einstein. It's called Bose-Einstein condensation, but actually, more importantly, he discovered an entire class of particles. I said Higgs boson, right? The word boson comes from actually Satyendranath Bose. And all the particles in the universe are of two kinds, either bosons or fermions, and he was the first to find out the behavior of this entire class of particles. So it's a very important contribution. More recently, Ashok Sen, who used to be in TIFR, now he's at the Harish Chandra Research Institute in Allahabad, has made remarkable contributions to our understanding of the fundamental laws of nature. He got the Breakthrough Prize in 2012. The Breakthrough Prize is regarded now widely as the equivalent to the Nobel Prize, but for more theoretical work. And he's one of the very few people who has received the Breakthrough Prize, and the only one from India. So the tradition of great theoretical work also continues. Now let me tell you about some experiments to come, which are also very exciting. India is going to play a key role in them, and in the next decade, big things are going to happen. Okay, and this has to do with gravity wave detection. I don't know if some of you heard about this. About now a year or more ago, the LIGO experiment, Light Interference Gravity Wave Observatory, detected gravity waves. Gravity waves are the analog of electromagnetic waves, and they were predicted by Einstein in his theory, but it's almost taken about 100 years after the prediction to find them. This is because they're very weak, very faint, and very hard to detect. But amazing instruments have been built using the idea of interferometry, which have allowed us to make this very important discovery. So here is one of the discovery was made using two interferometers which are on opposite sides in the United States. Again, the idea of separating them is similar to the idea of separating the antenna of the GMI. Okay, and in this case they are across the United States. But actually, it was felt that, in fact, if you had a third interferometer, which is as far away from the United States as you could be, then you would improve on the sensitivity even more, because in a sense you'd be able to look at the same object from far enough away, here from Earth, so that you can combine the data in a meaningful way. And so, of course, they looked at which could be a country, promising country about as far away as you could be from the United States. And of course, that country is India, right? We are among those countries. So we were approached, and the Indian government, I have to say, very, very responsive. In fact, I must say that I was really surprised about this because oftentimes, scientists get an idea, they get excited about it, they knock on the doors of funding agencies all over the world. But there are all kinds of constraints and you don't get what you want. And this was true in India, we were going around. And then we got a query from the Prime Minister's office. And we were told, we've heard that there is this remarkable observation which has been made of the first gravity waves, and perhaps India is keen to get into it. Is it true? And it was quite remarkable. I mean, with all the pressures that are there. And so the funding has come through. India has joined the LIGO collaboration, and the third arm of the interferometer is coming up now in India, in Nanded, and the Department of Atomic Energy, which oversees TIFR as well, DRC as well, is the nodal agency for building this interferometer. And I think in about 3 years or so, we hope it will start taking data and contributing to these remarkable discoveries. Just to tell you, so the first discovery was in 2015 of gravity waves, as I said, with 2 detectors, and the event is really as one of these amazing events. 2 black holes, each about 30 solar masses, 1.3 billion light years away. These are cosmological distance scales, right? Total observed universe is about 13.5 billion light years in size. This is about 1.3 billion light years away. Which the 2 black holes were moving under each other's gravitational influence, merging together, and as they merged, from the space-time itself, which got distorted, as Einstein has told us, came these gravity waves, which then traveled 1.3 billion light years into the interferometers and was detected. Very remarkable. It's a little bit like how you produce water waves. The water waves then make their way interfere and dance. Indian scientists at the International Center for Theoretical Sciences of TIFR, this is located in Bangalore, one of our newer centers, made very significant contributions in terms of computing from Einstein's theory what the signal should be, which can then be compared. Because these are not easy calculations to do, you need some intelligence. But Einstein's theory has agreed beautifully, really beautifully with these observations. So that's very interesting. As I said, we hope for the LIGO detector in India to be built in about 3 years' time scale. This is an artist's sketch near Nanded, and that's going to be amazing for all of you to play with and with all kinds of great sounds. Okay, I'm going to give you a few examples from biology and chemistry. I hope I can take another 10 minutes or so. And then I have another small component to the talk, but we can see. Here's a very interesting work done by Ruth Malik, one of my colleagues here in TIFR, explaining who's trying to understand the role of cellular motors. The cell actually is a very complex beast in its own right, because it has all kinds of organelles inside the cell. Those organelles play all kinds of interesting roles so that the cell can carry out its function. And one of the things that the cell has are actually molecular motors. Motors which actually allow various things inside the cell to be moved around, to go from one location to another. And here what we found was that the dynamic motor, which is these motors, can connect up to a phagosome which can ingest something bad and then take you to a lysosome which can kill the bad stuff inside. Okay? And this mechanism, this role that the phagosomes play, actually is aided by cholesterol. That is, the efficacy with which the molecular motors can latch on to the phagosome actually depends on there being enough cholesterol in the body. So, next time you're not eating your yellow of the egg because the doctor told you not to, maybe you should relent and have it anyway. No, we don't take that seriously. But cholesterol plays a very interesting role, mixed role inside the cell, and that's the kind of thing we're trying to do. The probes he's using are optical traps. It's a very interesting. You use a laser and you create through a laser a kind of pressure, and that pressure allows you to then trap a cell organelle or a molecular motor, and then as you move the trap, you can move the motor. And so it's this kind of very exquisite control that you can study what happens inside the cell. This technique of using optical traps was actually first developed by Arthur Ashkin. I thought I should mention that because he just got the Nobel Prize last year for exactly this discovery. And what Luke is doing is using it very cleverly to understand what goes up inside the cell. And there are all kinds of other applications also that people are exploring worldwide. Okay, two examples from chemistry. Vivek Shettiwar is studying something very interesting. You know, as you know better than me, it's very important to ask how can you get catalysis to work more efficiently in chemical systems, right? And one of the ideas many people have played with is to have a porous material so that stuff can get into it and get trapped there and then can be more effective as a catalyst. But Vivek had the opposite idea. He said, suppose instead of having pores, I have dendrites, okay? I have stuff that looks something like this, many fiber-like things coming out. This is in silica. So that the total surface area is very large. Okay, that also provides a way by which an agent can then get trapped in these big fibers. And that's the kind of material he developed with a huge ratio of surface area to volume. And that's been found to be very, very useful in various kinds of catalytic reactions, which can then be used for many interesting kinds of chemistry, from solar energy to sensory and drug development. And he's been trying more recently is to develop a kind of cycle of sorts where you take solar energy, combine it, and get some methane and get some energy out using carbon dioxide. So you get rid of the carbon dioxide and you produce renewable fuel. Of course, many other people are trying it in various ways. This is a key thing, but he's trying to use his own kind of material, as I said, is dendrite fibers for that purpose. The other example I thought I'd tell you about is work done by Angona Datta. This has to do with chemical chelation. Chelation island, okay, means to grab stuff and hold it. And so the idea is that you create a chemical compound which is efficient in capturing even trace elements of metals, manganese or copper and so on. And what that allows you to do is, if you can perfect this, is put it into a cell and that traps these unwanted metals, can sometimes help cure diseases, which can occur even if you have very, very small amounts of these unwanted metals. And so that's the technology which is developing. It's worked quite well in the laboratory, but we have to see whether you can actually take it to the next level into the clinic. So that's kind of interesting to exciting. Which is a big group. And we're looking forward to it. Last example, very interesting work from the National Center for Biological Sciences. This is Shiv Prasad, and I'll stop. It's very interesting what we are learning about DNA and RNA as we go ahead, because of course from Watson and Crick and thereafter you'll be like, okay, there's DNA, there's RNA and so on. But there's not just the RNA which plays the role of being, the messenger of the basic DNA so that it can be converted into protein and so on. There's much more structure to the RNA. There's what's called small RNA, which plays more of a regulatory role. And what Shiv Prasad has found is, if you can change the small RNA, you can give rice plants much better mechanical strength. So what was happening with rice was that if you tried to improve the productivity, then the stalk would get heavier because there was no grain. And rice, of course, as you know, has to be grown in water, so the land would lodge down and then, it would get destroyed before the grain could be fully ripened. And what he's found is that you can improve the mechanical strength by playing with the small RNA, which he can manipulate genetically. And that can lead to really much better productivity for rice. And now he's trying it for other kinds of plants as well. So this is an example where as we understand the genetics at a much, much deeper level now, finer level, we can do that. I have many much more examples there, but I'm going to go. Quantum computing is actually very, very interesting. Huge progress. Very, very exciting group here, led by Vijay Radhan, working on superconducting qubits. Very promising for the future. Okay, we'll see. So here's, all right. I want to show you this. I have to show you. This is the quantum computer, 3-qubit machine. Small but can be scaled up in TIFR. Here's a 5-qubit machine of IBM. Never mind the details. Success probability means how well you're doing for implementing some algorithm. It's actually a very famous algorithm developed by an Indian computer scientist. Here's the Indian machine, 49% success. Here's the IBM machine, 39%. Okay, not to say too much rah, but just to tell you, I mean, this is the point I want to make. See, you can really do world-class comparative science. Okay, you can really do it. It's no longer the case that you have to go abroad, you have to do that. You can be here and the opportunity is there to you. So you know, I think let me try and stop here just to say it's a very exciting time for fundamental science. It's very exciting in terms of the startup environment that exists. There are 40,000 startups in India. The real challenge is how do you translate something that's in a startup, in an incubation stage, into industry. But we are slowly getting examples of that, and you know, there's reason to hope. IIT Bombay has a very good startup incubation center. We have one in Bangalore and so on. So you know, I think it's very, very exciting. I want to end by just telling you, you know, there's something else I want to say to all of you. Why it's very important to try and work in India. Because you know, none of us is just about eating our food, even doing our work. But there's an element about being inspired. And this is what I tell our young faculty. Oftentimes they're trying to weigh between should we stay on in the US or Europe, should we come back to India. And you know, the fact of the matter is, when you work from India, you join yourself in this larger quest of a country, trying to come of age, right? Trying to do the big things which we should do, which is rightfully our place to have done, but for some blips in our history, right? That is getting corrected. We stand at this great threshold, as I said to you. You see the change, right? The opportunities are there, the young people with all their talent are there, and I think really nothing is going to stop us in the next decade or two. So there's tremendous progress, and I think you should try and do it. Do it in our country. Of course, go abroad, travel, you know, let the world come to you, do good to the world, but things don't lose track of your country. So let me just end. I think there's going to be remarkable progress. I think India is going to play a big role. Young Indians are going to play a key role, and they must, because without that, the key problems which we face won't be solved. And in so doing, they will transform. Okay, thanks a lot. You can ask questions if you have for some. Sorry if the talk was a bit too rah-rah, you know, everything is good, but we hear enough about the other sides, about what goes on elsewhere, which is also exciting. But if you have any questions, I'm happy to. Or any general questions, also not tied to, if you have any questions about science, pursuing a career in science, or anything else, I'm happy to answer that too. Opportunity, yeah, go ahead.
So isn't it important when you are pursuing PhD? So when you are actually doing it, you may not get it in the first shot. So as you move on from one failure to the next, what is the thing that helps you most? Is some kind of hobby that you need to do? Or
what helps you most as you try again before you succeed? Yeah. Well, you know, different people have different strategies for science. But I think one thing which is common is that you have to persevere, as you said, but you shouldn't persevere in a foolish way. You know, in other words, you have to keep, this is at least the way I would put it. When you do your research, let's say it doesn't work the first time around, you have to assess what went wrong. This is why, you know, it takes time to become a good researcher. Because what you're trying to understand is by definition something you don't know well. Plus, there could be, you know, as was said, there are the known unknowns and then there are the unknown unknowns, right? There are the things you don't even know about that you don't know about. And where do you place your doubt? Let's say something doesn't work, right? Where do you place your doubt? That's what takes time, that's what takes judgment. But usually it is a combination of your knowledge and your experience, and also it's very important to take feedback from other people. You know, science is an open process. This is also very important. To be able to discuss your ideas, to be able to get the input and assess it, that's also very important. last of all, I think what's very important is to have people with a fresh mind in a non-hierarchical way working together. This is very important. See, when you do research, there's actually no, like, so-and-so is the professor, therefore what he says must be right. That kind of thing is like the kiss of death for any research enterprise, right? My students never hear what I say. In fact, oftentimes they'll say, it's a good thing he was away the weekend, we could discuss it amongst ourselves. Otherwise, he would come and, impose his ideas on us, So, there's a very open atmosphere, you get the input, you assess it, you go forwards. Now, of course, you don't always succeed. Sometimes there are, for example, in any experiment, there is some hidden aspect which is corrupting the experiment, some noise you can't control, some impurity which is entered which you don't quite know the cause for, some extraneous signals which are coming in. This can happen despite your best attempts, but if you take all these precautions and so on, you have a good chance of success. Now, if after trying long enough it doesn't work, then of course there's also a judgment call in the world to say, look, it didn't work, maybe we don't understand why, let's move on and we'll come back to it. So it's some combination like that. But it is a bit of an art, I would say. That's why you don't just learn it. There is the aspect of, research is a little bit like learning any really advanced kind of knowledge system. If you learn music at a high level, you can't open a book and learn classical music, right? Because you have to learn it from those who do it at the highest levels. And it's the same with science.